the database inner working. Now we will start opening the engine and seeing how things work inside. We will be doing it in the class. We will be doing it for relational databases, disk-based relational database, and some of you will be doing the same exercise for non-relational database. Some of you taking let's say in-memory database. So some of the mechanism will be different based on the nature of the database. But the one we will be discussing here are disk-oriented relational databases. And we will be covering four major topics. First, we need to understand the storage technologies that are typically used by relational database. And this understanding is very important because the understanding of how storage works and the difference in speed between the storage types influences the design of the database, as I will be explaining. Part of the storage technologies, we really need to be at least be aware of these RAID technologies that are heavily used in practice when we manage and store databases. Finally, in the database, we need to see how database stores data in files, how files are organized, and what are the mechanisms used by the database to organize data in files. And the last topic will be buffer manager, which I will explain what it is and what we need it for. So those are the main four elements I'll be discussing in this session. But before that, I just want to highlight when we talk about inner working of a database, these are the major topics. Yes, please. Yeah, I think I did some changes. Sorry, if you don't mind, I will just post this. Let me see. Just want to see here. Okay, I'll stop it here, 57. Give me 1 second. So when we start talking about the inner working of the database, these are the typical topics that we will be covering. We will be covering how the storage works, the storage engine in the database, how does it work, and what are the major components of the storage engine. And in the storage engine, we talk about three things: the disk manager, the buffer pool manager, and access method. These are indexes. We'll be covering in future weeks. Once we know how the database stores data in files, we'll go ahead and see how queries get executed in a database engine. And then how consistency and isolation is preserved when we have multiple concurrent users. And this is known as concurrency control. And finally, recovery. This is to achieve durability, if you recall. So in these topics, we will be covering some high-level understanding what they mean, and then focus more into how the database delivers these basic functionalities to deliver a database, relational database engine. These are the components of the engine. And we'll take each component at a time, and we will be diving into its details. So every topic will take us 1 or 2 weeks to cover. Okay. So today we will be, inshallah, starting with the storage engine, which is dealing with how the data is physically stored in files. So as I explained, we will be focusing on disk-oriented database because lately, because the development of the memory and becoming more and more cheaper, some databases can fit fully in memory. And they can be fully managed in memory, and they call themselves memory-based databases. Those are not within the scope of this discussion I'm discussing today. What we're discussing today is disk-oriented database, which means that the database is physically stored in disk, and then, of course, we bring it we bring the parts that we need to the memory to process it and to query it and to modify it. And the major components of the storage engine, the main role of the storage engine is to manage the movement of data from disk to memory. You know, in a disk-based database, we cannot do processing on disk. We all know this. In fact, this is true for any program or data we want to process in a computing system. We first need to bring it from disk to memory, and then from memory, that's where we store the program and the data we want to manipulate. Now we have to do it in a very smart way and a careful way. Otherwise, we will end up with large waits, or we will introduce delays, or we might have performance degradation. And I will explain why. So the storage engine has two goals. Two goals the storage engine has. It helps us to manage databases that exceeds the amount of memory that we have. So typically, it is still the case for most databases. The database we're trying to manage is larger than the memory we have. So there is a challenge here. We cannot fit the whole database in memory, so we have the full database in disk and part of it in memory to do the processing. Now, because, as I will explain shortly, disk read and write is very expensive. So this disk read and write need to be managed carefully in a way not to degrade performance. So these are the two goals of the storage engine. Help us manage a database that cannot fit all in memory, and help us to do a read and a write in a smart way, in a way that will not degrade or reduce the performance of our queries. So those are the two major goals of the storage engine. Now, before we dive into how the storage engine works, we have to start talking about the storage technologies that are used in the database world. First, we need some motivation. Why? First of all, we need to worry about the physical level of the database. Why do we need to worry about understanding the storage engine and how the database manages physically the data on disk? This is very important for many reasons. One is someone out there has to write the storage engine. So they need to understand it for them to be able to write it. That's one reason. The second reason, some databases, they give you different ways of physically storing the data. For example, some databases, they call themselves row-oriented storage versus column-oriented storage. Maybe you might come across this while doing your reviews. Some databases are column-oriented and others are row-oriented. How do I choose between these two storage models if I don't understand what they mean? Yeah? So sometimes there are some choices given to the database administrators, and they need to make an informed choice. Also, for an experienced DBA, for them to really tune the database, to squeeze from it the best possible performance, they really need to understand what's happening at the physical level. Okay? Although we understand from the few lectures we did in the beginning that the database liberates us as developers from knowing the physical data storage and the physical layouts and the physical level. We just need to know the schema, which is a logical data model, and we need to know a query language. That's enough for us as developers. But for database administrators that are responsible of keeping the database running to the optimal speed possible, they need to configure it in a proper way so the database behaves in the best possible way. And for them to do so, they need to have a good understanding of the physical level. Finally, some of the techniques and algorithms that are used in the database world can be applied in other scenarios, in other contexts. Okay? Okay, so this is the motivation of doing it. Second thing, why we start with the storage engine, and we need to have a good understanding of it. The storage engine is the one that is contribute the most to the overall performance. If you have a crappy storage engine, your database will be very slow. It's the most important component that delivers a good performance of your queries. And when I say performance, basically there are two metrics that define performance. Two metrics. What are these two metrics? This is not specific to database. This is very general. When you hear this word performance, it has, yes, the speed which is also known as the response time. This is the time when you submit a query to the database and the time you start seeing some results coming back. The interval of time between the submission of a query and the time you start getting results, that is basically the response time. What is our goal in the storage engine design? We want to minimize that response time. The other metric that we care about when we talk about performance is the throughput. Okay, the throughput is usually measured in terms of how many units of work a particular system can complete within a unit of time. For example, how many queries can be executed per minute or per second. So that's the throughput. And for the throughput, what is our goal when we design our storage engine? Maximize the throughput and basically minimize the response time. And the whole database engine, the core component that is responsible for or that contributes the most to the query performance is the storage engine. And we will see shortly why so. Okay, so for us to understand this, we first need to revise, maybe some of us already seen this many times, the storage hierarchy in a computing system. So the storage hierarchy, you can divide it into two major blocks, if you wish. There is the volatile random access memory, and there is the non-volatile sequential access block addressable storage. Okay, so the volatile parts includes the RAM, CPU caches, and CPU registers. Okay, as far as the database is concerned, it's enough for us to just divide this storage hierarchy into two parts. There's the memory part, which is volatile, high speed, and random access. So in memory, it's not you can access any byte in memory randomly, and there's no cost in doing so. But in disk, it is very costly to start reading blocks at various places. I will explain why shortly. But first of all, in here, when we talk about memory at this stage, we can read and write even at a byte level. We can read 1 byte, we can write 1 byte. In this non-volatile part, if we are lucky to have some SSD drives, solid state drive or hard drives or network, even a network storage, in here we don't talk about bytes, we talk about block. And usually in databases, in practical databases, the block size is from 4 to 16 kilobytes. So what is the minimum unit a database can read and write to disk? Is a block. And what is the typical size of this block? 4 to 16 kilobytes, based on every database has this size, different size. Okay, this is very important. So when I read a record, I cannot read a particular record, just one record. Usually I read the whole block, and the block might have multiple records. So keep this in mind, because at this level, I mean below the RAM, the access is much slower, although the capacity, the storage capacity is typically larger and cheaper to buy and maintain, but it is slower to access. So when we access, we don't access small little piece of information. We access a block, we read it to memory, we modify it, we might query it. Especially if we modify it, we write it back as one block. So the unit of reading and writing in a database is a block, not a byte or not a record. It's a block. And this block is fixed size. So each database has its own fixed size block. Okay. Now in here, as I mentioned, jumping from one block to another randomly on disk is very costly. While reading any location in the RAM randomly is the same. There's no cost in doing so. So in here, sequential access is much cheaper, and it runs much faster than random access, which means as much as possible in the database storage, we try to keep the records that are related. Sorry, we try to keep the records that we need for our queries next to each other. So when we read one block, the next block we need ideally is supposed to be next to it, okay, as close as possible, so we don't keep jumping over the disk. And I will explain why this is important. So that's what you need to keep in mind from this diagram. And also for the future, this is more future generation databases, that there is a new type of storage which is known as non-volatile memory. So this has been going on in research and development for more than 20 years. But lately, there are some products out there from Intel. I included a video here where you can have a non-volatile memory, which means a memory that can be randomly accessed, byte addressable, very super fast, at the same time non-volatile, which means it keeps its content even in case of power is off, or you take power off and it keeps its content. So, but of course at this stage it is still very expensive, still new, but in the future that could be the future storage, and that will change the whole thing. The whole game will be changing. Okay. So to summarize, as far as we are concerned in terms of database design and storage engine design, we just need to distinguish between memory, which is fast and volatile, and disk, which is slower and non-volatile. That's the main message here. Now, in terms of storage hierarchy, we can divide it into three levels. Like primary, what we call primary storage, secondary storage, and tertiary storage. Okay, so the primary storage includes the cache and the memory. Cache and memory. So for the cache, especially those from CE background, maybe they will have a much better background than me on this. So for cache memory, even when we want to buy, like, let's say a laptop or something, you might see this in the specification of the device you want to buy. So you will find L1 cache and L2 cache. So those are memories, super fast, but very limited capacity. Capacity usually measured in megabytes. And the access time is a fraction of nanoseconds to nanoseconds. Super fast, but the capacity is very, very small. So the L1 cache, you will find the memory chip in the same chip as the CPU. And L2 cache, it will be on a separate chip, but very close to each other, physically very close. Now the main memory, this is where as you know, all the programs and data need to be transferred from disk to the main memory for them to be processed. Now L1 cache and L2 cache are used for just the, let's say, the instructions or the data that is needed for the current operations being executed. So you can think of it this way. Your database, the full database must be stored in hard disk on SSD, full database. And then part of it will be in the main memory. And maybe small little part of it will be in L1 cache or L2 cache. So you can think of it this way. So the full database is here, and part of it is in memory. At any time, if you take a snapshot, you will see the full database in memory, full database in disk, some parts in memory, and some parts in L2 and L1 cache. In fact, this is ignored, not really. This is the most important. And at this level, in the RAM, we have what is known as the buffer manager. And database manages this buffer manager. And I will explain this later, okay? Now, in terms of secondary storage is still, by far, these days, still disk. Although SSDs are picking up, but still, in terms of capacity, they are still smaller than the hard disks and also more expensive than hard disks. For tertiary storage, they include offline storage. These are backup tapes. Usually, they are not used for online storage, not like hard drive. They are used for offline storage, maybe for backups of older versions of the database. So those are the main storage hierarchy. They are in here in the primary storage. We're talking about few nanoseconds to read and write data to these primary storage. In the secondary storage using magnetic disks, we're talking about milliseconds. And for storage on large capacity tapes or large capacity tape or optical storage, we're talking about seconds and minutes. Okay, so these are not suitable for online, mainly for archiving. Okay. Now, what we also conclude from here, there is a major speed gap between these various levels of storage. This gap creates a major challenge. So there is a speed gap between memory and disk, and this gap need to be taken into consideration. In fact, as we will see moving forward in the query processing, when we want to measure the cost, how much a database operation costs, the unit of measurements of a cost of a database operation is basically the number of disk IOs or the number of blocks you will be reading and writing. So you can ignore all the CPU processing and all the transfer to memory. Those are negligible when you compare them with the disk IO. So, for example, when I say, when I want to read, let's say I want to get the transcripts of a particular student, that will be a query. If I want to cost that query, how much that query will cost, I will say to you, for example, that will require reading 5 blocks. That's the cost. So because of the speed gap, we can basically ignore all the computation that takes place here. It's negligible compared to reading from disk into memory. So the cost of a database operation is measured as numbers of disk blocks that we read and write. Yeah, that's how we measure them, and we will see this as we move forward. If we have a query and there's multiple ways of running the query, how we will choose which algorithm or which strategy we will run the query. If we have multiple plans or multiple ways to run a particular query, what do you think? How we will choose which query plan will be better? The one, sorry?
Which will use the least block IO.
The least block IO. We don't need even to think about how much computation it will need, how much memory, how much processing that will require only memory. We can ignore all of that. We just cost those two plans. Yes, how many blocks we need to read and write. That's all. Okay. Now, in terms of relative speed, this is available in this URL on GitHub. So those are some measurements, some real measurements of how long it takes to read and write a block to one of these memory, one of these storage options. So you can see there in L1 cache and L2 cache, we're talking about nanoseconds, and in other devices, we're talking about seconds. So because these numbers are too hard for us to kind of comprehend, if we scale them to seconds, then the difference will be much clearer to us. Yeah. So for example, in here, look at the RAM, for example. It will take 100 seconds. Doing the same thing from an SSD, it will take 1.7 days. Using hard drive, 16.5 weeks. And using a tape archive, will take 31 years. Yeah. This is just to highlight that between two layers of storage, the difference is thousands of magnitude. Like the difference is very, very significant. That's what this diagram is trying to tell us. So each level is thousands of times faster than the level below it. Okay, so that's why later on as we move forward and we say that the performance of the whole database is measured by, is dominated by the cost of input-output. That's the most important part that determines the performance of your database, is how much, or performance of a particular query, is how much disk I/O it will require to answer it. Okay, now, moving on, I think since hard disks are still the most important storage technology used to store databases out there, although this is slowly changing to SSD drive, slowly changing to non-volatile memory, slowly changing to database that run fully in memory. But by large, the disk-oriented hard disk-based databases are still dominant. So that's why we need to spend a little bit of time understanding them, understanding the hard drives. Okay, and this will help us really design our storage engine in a better way. Okay, first of all, the data stored in a disk is managed using blocks or pages. As I explained before, these pages or blocks between 4 to 16 kilobytes. So unlike in memory, in the RAM, you can randomly read and write any bytes in the RAM. No cost, no extra cost to jump all over the RAM and get whatever location you want to read and write, because basically it is all electronic. While in the hard disk, especially I'm not talking about SSD drive, I'm talking about hard disks. They still have some mechanical devices with mechanical components. So the hard disk has mechanical components that I will be explaining shortly. And these mechanical components, definitely they need time. If you want to read kind of randomly, keep jumping from one place to another on disk, that will take time. So the hard disks are still more optimized for sequential reads. It will do much better job if you ask it to read this block and then read the block next to it and read the block next to it. You will get a much better performance than asking the hard disk to keep jumping from one sector to another to read your data. So we need to keep this in mind, and that's why as we move forward, the database tries its best to keep the blocks related to a particular table contiguous next to each other. So when we are answering a particular query, hopefully we can just do a sequential read rather than doing random reads on the disk. So the relative placement of pages, on disk makes a major difference on the performance of the database. Okay? Reading two contiguous blocks is far less costly than reading blocks that are in totally different places on disk. That's what we need to keep in mind when dealing with disks. Okay. Now, why is this? For us to really understand what's going on, we need to first just super quick anatomy of how a disk, what are the major components of a disk. So what we have here, so the disk is made up of platters, so kind of layers upon layers. They have two sides, each platter has two sides. And then what in the disk we have this arm, okay? So first of all, these platters are connected to this spindle, so something that keeps spinning, and these platters basically keep rotating. That's why when you buy these disks, you can see the RPM per minute, or the number of rotations per minute. So one of the specifications, 15,000 RPM or 7,000. The faster it rotates, the better. Okay. And then we have this arm. So we have an arm that goes over these platters. And this arm, for example, if I want to read certain block, I move the arm and I wait for the sector that containing the block to come under the arm to be able to read it. Okay. So to summarize, I will give you further details, of course, but for now, from this picture, what we want to understand is the disk is made up of platters. Think of them as kind of, let's say, what they call themselves, the CDs, let's say. Think of them as a stack of CDs that has two sides, okay? And then we have an arm that moves across the disk, and then the arm will wait for the data that we want to read until it come under the head of these reading heads for us to basically read the data from the disk. Okay. So there is a mechanic. This part here is a mechanical part. So it's a physical movement. It's not electric. It's not electronic or electric, which is super fast. This is mechanical. That's why it is this disk movement, this arm movement. It takes time. It's costly operation. Okay. So the disk consists of platters. Each platter has two surfaces, and each surface is made up of tracks. So here is the surface, and tracks are those circles here. This is a track, this is one track, this is another track, this is another track, and so on. Okay, so those circles are basically the tracks, and each track is made up of sectors. Sectors, we call them sectors. Okay, so that's the composition. So we have platters. Platters are divided into tracks, and tracks are divided into sectors. Okay. Also, there is something called cylinder. Cylinder is something imaginary. So all the sectors that are like on top of each other, belonging to different platters, they form what is known as a cylinder. So that's basically the major ideas here. And by the way, although we have many heads, so each platter, if you look carefully here, we have many heads. On each surface, we have a head that is able to read and write to sectors on that platter, but only one of them will be working at a time. Not all of them working simultaneously. Only one. Only one head read and write at one time. Okay. So what we have here, this is a view of one single platter. single platter made up of tracks, and the tracks are divided into sectors. And basically, these platters are attached to a spindle that basically rotates them. So these platters are rotating all the time. And we have the arm. We have basically the arm, and this arm, to the arm we have attached the heads, and the arm moves the heads across the platter in this direction. So they can move this way, okay, back and forth. Okay, now when we want to read or write to a disk, the time it takes can be divided into 3 parts. The time it takes to do disk access is made up of 3 components. The time it takes to read a particular block in disk is made up of 3 components. The first component is called the seek time. So the seek time, this is the moving the arm to the position, to position the disk head on the track. So the movement of the arm on top of the track, that is the seek time. Yeah. So we know that we are looking at a particular block, and that block happens to be, let's say, that block happens to be in this sector. That block happens to be in this sector, in this track. So we have to move the arm, to place the arm on the sector. Yeah. And then there is another time that's composed this disk access is the rotational latency. So we place the arm on the correct track and then wait for the disk to make the spin for the block we want to read to come under the arm. So there is the seek time to move the arm. There is the rotational latency to wait for the block that we want to read to come underneath the arm. And then finally, this is the least cost, which is the data transfer. Once the block we want to read is under the arm, we read it, we transfer it from disk to memory. So these are the 3 components that make up the disk access. Okay, and the most expensive one is definitely the seek time, because it requires a physical movement of the arm, plus this rotational delay, which require again a physical rotation of the platters, and finally the transfer is the least costly. This will depend on the bandwidth of the hard disk. So in the specification of the hard disk, it will tell you how many megabytes it can transfer per second from disk to memory and vice versa. Okay. So this is what I mean. If you have some block that you need to read on the same track, so you don't need to move the arm again. You just, hopefully you can just, the next one will, this is the disk rotates, or the platters rotating. You have the block here, you read it, the next block will be just contiguous to it. If you are lucky that way, you don't need to go through this again, this costly operation. That's, sorry? For that, that's why, as we move forward, as we will see in indexing, as we will see in the data file organization, database strives always to keep the blocks belonging to the same entity or belonging to the same index contiguous, physically next to each other, to avoid this seek time. Yeah? To just wait for it to become beneath the head without moving the head, and then the transfer time, which is not that significant. Okay, so the access time, as I explained, is made up of seek time. According to some of the studies, like it takes between 4 to 10 milliseconds, rotational delay 4 to 11 milliseconds, and the transfer time or data transfer time depending on the rate, depending on how fast the rate of transfer of the disk. So the access time is dominated. The access time is dominated first by the seek time, Why is it dominated by the seek time? Because the seek time requires a physical movement of the arm. Okay, then the rotational latency, which requires rotation of the platters. So this is the first component, the most expensive component, followed by this. Transfer time is not that heavy. Okay, so to summarize, the disk speed is dominating access time. The time it takes to read and write is dominating the whole access time. That's why, first of all, database does a couple of things to speed up this. First of all, we read one block at a time. We don't read small pieces of information. As I explained, from 4 to 16 kilobytes, that's the unit of reading and writing. Plus, as I explained, database strives to keep the blocks contiguous, so we don't need to do. We can save on seek time, and it does some other tricks that I will be explaining as we move forward to basically offset this dominance of disk I/O. There are some techniques to do this. So to optimize, these are the three major techniques that modern databases are using to minimize the time spent on waiting for disk access. Three major techniques. One is to store related data on the same or nearby blocks. Keeps the data in contiguous disk blocks. And to do so, that's the role of database administrators. They always reorganize the physical data storage so the database can the blocks are contiguous. This will become clearer as we move forward. You will see when we start inserting into some database blocks. Sometimes the block, we need to split the block. And one block will be here and the other block will be far away. We cannot reorganize online the database because that will slow down our database. So we do this reorganizing the blocks, we do it offline. So that's why in many commercial databases, there is a big role called database administrators, and that's what they do, is to make sure the database is optimized to yield or to provide the best possible speed for our queries. And one of the tasks they do is they do physical reorganization of the storage. Physical organization. Of course, there are commands in every database. There are commands that help you to do this, but you have to schedule them or you have to do them regularly to make sure the blocks are contiguous. And to make sure, for example, if we have a lot of deletes, some blocks are empty, we're not going to reclaim when we delete something, we're not going to reclaim the space immediately. We just mark the records as deleted, and then later on, we will reorganize the actual blocks of the database. Okay? Similar to disk, sometimes your machine starts getting slower and you do some disk defragmentation. There are utilities that come with Windows and your operating system that help you to do this. Kind of similar. In here, we need to periodically reorganize the database blocks or the data file blocks to make sure they are contiguous. Second thing database tries to do is to keep frequently or recently accessed data in the buffer. So that's why one of the major components of a database is the buffer manager. So when we read blocks, we don't just get rid of them immediately. We keep them. Okay? Now, when we keep them, of course, we will run out of memory at a certain stage, and we have to evict or kick out some of these blocks. Now, there's another challenge. How do we choose which block to evict from the buffer? That's another challenge that the buffer manager tries to address. So here, this is the role of the buffer manager. You need to have some smart algorithms in the buffer manager to keep the blocks that are more likely to be used by future queries in a way to speed up such queries. And finally, another technique that databases use is parallelism. Parallel writing and reading to disks. And this parallelism is basically achieved using RAID technology. In professional databases, almost 99%, if you have a professional database in an organization, in professional context, you will have some kind of RAID. It's not just simple disks that we have in our laptops or our machines. Any idea what this RAID stands for? Sorry, have you heard of it? You have used it? Yes, please. Yes, so it's an array of independent disks or an array of inexpensive disks that are put together and they act as one. And we will, of course, discuss them. So this gap in speed between the memory and the disk is a major problem in the storage engine design. Okay, and we need to do something about it. So database, or the storage engine in particular, uses these three major techniques to help address this speed gap between memory and disk. The first technique is to try to keep the blocks related to a particular entity or to a particular index, keep them contiguous next to each other to avoid the seek time and the movement of the disk arm. Second is to manage the buffer in a smart way. When we read some blocks in memory, we keep them there with the hope that they will be used for future queries. And when we want to evict or kick out some of them, we need to do it in a smart way. And the last technique is to do parallel read and write using RAID. Those are the three major techniques used by databases to address this speed gap between memory and disk. Okay, so this is just to highlight the importance of having contiguous next blocks or blocks that are next to each other. So let's just take a very small example here. Let's take an example where the seek time is 10 milliseconds. This is time it takes for the arm to move to the correct track to read the block that we want to read. And the average rotational latency, which is the time it takes for the platters to rotate and come under the head for us to be able to read. That's 3 milliseconds. And the transfer time for one block is negligible, like less than 0.08 millisecond, okay? Now, if the blocks are adjacent, which are basically contiguous next to each other. So all we do is on the same tracks. So adjacent blocks on the same tracks. So we need basically to have 10 milliseconds here for the head to move, then 3 for the rotational delay, then basically we don't need to repeat this. Yeah. We don't need to repeat this because the blocks are contiguous. So we only need to multiply, because we have 2 blocks, we have transferred 2 blocks, we just multiply the cost, the transfer time times 2. Yeah, this is for adjacent blocks. Now, if they are random blocks, guess what? This needs to be repeated again, and this needs to be repeated again. And of course, this one. So we have to do the sum of this times 2. You can see already double the time it takes to read blocks. Random access versus sequential access. Oh, okay. Now, in memory, we don't have this problem. In memory, you can jump from one area to another without any extra overhead. In this, that's a different story. Very, very different story. Okay. Now, I think I will stop here for maybe 10-15 minutes, and then we'll okay. So as I discussed, in term like to address the challenge of the speed gap between memory and the disk, database uses three strategies. One is keeping blocks contiguous next to each other. Second is efficient management of the buffer pool. And the third is parallel I/O, parallel read and write. So for parallel read and write, this is where RAID technology comes in. So those of you familiar with it, you can please contribute, because for me, I never worked with it. But in database, you cannot talk about database storage without at least being aware of such technology. Okay, so RAID, it allows us to do parallel disk access, and RAID stands for Redundant Array of Independent Disks. Usually in the past, they used to call it inexpensive, but this is the kind of the terminology evolved to independent. So redundant arrays of independent disks. So basically, you have an array, you have a set of disks acting as a single high-performance logical disk. That's what it is. So it gives you higher capacity and higher speed and read and write, and also higher availability, depending on the configuration of the RAID. There are many configurations, but usually in high level, we use the RAIDs, first of all, to do parallel read and write, to have higher capacity, to have higher speed, and sometimes even higher reliability. And it helps us to reduce the speed gap we suffer from between disk and memory. So there are many configurations out there, and we use them. Companies invest in RAID for two main reasons. One is to improve the throughput through parallel read and write, and the other one is to improve reliability via replication. Okay? So these are the two major reasons why companies invest in RAID. It can be a combination, and or. So to improve throughput through parallel read and write, and to improve reliability through replication. Okay, now the way you organize, the way you configure this array of disks is, there are many ways of doing so, and each famous configuration, it has it codified with a number. So there is something called the RAID 0, which is also known as striping. RAID 0, also known as striping. So it requires a minimum of 2 disks. And what we're doing here is that if I have these blocks A1 to A8 to write, I basically write block 1 and 2, block 1 in disk 1, block 2 in disk 2, block 3 in disk 1, block 4 in disk 2, and so on. Okay? So if let's say I have here, I'm inserting so many records in a particular table, and this generates many blocks that I need to create. So I can do this in parallel. Half of the data will be written in one disk and the other half in another disk. And this read and write is much, much faster, because I have two disks with 2 heads and basically 2 disks working together as one. This is called striping. Yes, please.
So it's like a scale up with 2 disks?
Scale up. You can think of it that way, scale up with 2 disks. In here, okay. Yes, first of all, what is the capacity of the disk array in this case? The capacity is the sum. If you have, let's say here, 1 terabyte, and this is 1 terabyte, what is your total capacity? 2 terabytes, okay? So when you put them together in an array, they become like a logical disk with a capacity equal to the sum of the 2, yeah? And your speed of a read and a write, suppose theoretically it should be halved. Of course, theoretically. So it will speed up your read and a write, and it will give you, if your database is large, cannot fit on one disk, you can fit it in multiple disks acting as one. Yeah, is clear this configuration? But what is the problem with this configuration?
The consistency.
No, there is no consistency problem, of course, here, because yes, if one disk is gone, you lost everything. You lost basically the data. You lost half. You cannot reconstruct your data. You خلاص, finished. It's very, very risky. There is no basically no reliability here. Okay. So you get high performance, of course, higher capacity if this is what you want, but you have no reliability, no improved reliability because there is no redundancy. It's even worse because if you lose one of the disks, you basically lost your data. But what is the advantage of using this configuration? Increasing, yes, boosting the speed of your read and write. So that's the first configuration, RAID 0.
So, doctor,
yes.
Like I have, for example, here 8 blocks. I will divide it into 2 disks, right?
We don't. This is just to explain the concept. We don't do this. There is an array, disk array controller. For us, even as developers, or even it's transparent. You only see it. You see this as one disk. You don't see it as 2 disks. There is a disk array controller. It could be software based. It could be hardware based. That is taking care of this. Yeah, for you just write, and the disk controller will do this for you, or read. It will do it for you. Yeah, it's transparent to the developer. This is all hidden from us. Yeah, it's taken care by the RAID controller. Okay. So this configuration is basically called the striping. It distributes in disk in a round-robin fashion across your disks. If you have 4 disks, you can also, of course, do that. You stripe your blocks across these disks. You can have as many disks as you want. Okay, but if you lose one of them, you lost your data, because you lost part of it, which means maybe the remaining is useless without the other parts. Yeah. So that's the first configuration. The second one is called mirroring, which is RAID 1. So the first one is RAID 0 striping, called striping, and RAID 1 is called mirroring. And as the name suggests, is a mirror. So each disk is the mirror of the other disk. So you're writing simultaneously 2 copies on 2 disks. Yes? That's the idea of this. So here you get what is the capacity of the disk array? The capacity of the lowest capacity, the disk with the lowest capacity, that is your capacity. Okay. If they are same, basically you have the disk capacity of 1. Yeah, because you are basically mirroring. So yes.
Why you say the lowest capacity?
Because, for example, this is 1 terabyte and this is 2 terabytes.
It's supposed to be mirror, the same.
No, what I mean, but you can only write. You fill up one. What I mean, it writes in both. Same. Every block has 2 copies here and there. So let's say, imagine this is 1 terabyte and this is 2. Can you use the other 2 terabytes of the other disk? You cannot use it because each block has to have a mirror of it, a copy of it. Yeah. So you get the right speed of one disk. Of course, you get the right speed of the lowest speed of the disk that is the slowest disk. That is your write speed, because you have to wait for both of them to finish writing each block. the read speed of 2 disks. Now for the reading, you can read from any of the disks, it's fine. You can imagine that if you have multiple queries, they can be served from different disks. Yeah. So the read is improved, and the capacity is equal to the size of 1, or to be more precise, to the size of the lowest one. So this is very popular for files that are very critical, that you don't want to lose. And in the database context, one of the files that is so critical is the log file. You may lose the data file, but you never want to lose the log file. Why is that?
It will contain all the updates that are not reflected
Yes, it has the entries that are not reflected back in the data file. Not only this, let's say people started working at 7 a.m. and then a crash happened at 10. Let's suppose, and you cannot recover the data file. If you have a log file, you can recover everything. What you can do, you can restore last night's backup. Hopefully you took a backup. That's what administrators do, by the way. It's their responsibility. If the backup failed if the database failed to backup, or you cannot restore it, they are in very, very big trouble. Okay, that's their responsibility. So even if people works from 7 to 11 or 10, let's say, and crash happen at 10, you are still safe if you have the log. You can restore last night's backup and replay the log, and you get the database up to the time of the crash. So this file deserves to be put on RAID 1. You need 2 copies. If one disk fails, you never lose your data. You can basically tolerate losing one disk. It's clear the idea of RAID 1 is mirroring, is the opposite of RAID 0, which is striping. If you lose one disk, you're gone, everything is gone. And here, you can afford to lose one disk, and everything will be fine. Okay. There is also this RAID 2, 3, 4. They are not practical, so I didn't even bother thinking about them. The most famous and the most widely used RAID is RAID 5. RAID 5, the way it works, you need at least 3 disks. Okay, it requires at least 3 disks. And what you do is, I think it's easier, let me explain it. There is something called parity that we need to explain, okay? So imagine here, imagine each letter here is a block. Just imagine each letter is block. And imagine you have an array of 4 disks. An array of 4 disks. Okay, so the way you do it, you will do striping. You will stripe the blocks. Striping means in a round robin fashion, you distribute the blocks across the disks. But one of the disks will be storing what is known as parity bits. So the parity bits this block here is computed by XORing at the bit level. You XOR this block with this block with this block. So you store here A, B, C, and the 4th disk will have the parity, which is nothing but XORing all the blocks that you stored in disk 1, 2, 3. Yeah. Then up to now, how many? Let's say how many blocks we have stored so far? Up to C. Yes. Now, next time, this parity block, I'll put it in the next disk. So the place where I store the parity block is also kind of a round robin. So last time I used the disk 4. Next time for parity, I will use disk 1. So D, E, and F will go into, respectively, will go into disk 2, 3, and 4. I store them in disk 3, 2, 3, and 4. And in disk 1, what I will store? The parity bits. What is a parity bit? XORing these guys. XORing these 4 blocks that I have, these 3 blocks that I have stored in the disks. Then I do the same. The next lucky disk that will have the parity is disk 2. So I'll be storing up to here, I'll be storing G, H, and I. So G, I skip 2 because that's where I'll put the parity block, and store H and I, and compute the parity block, and so on. Okay? So let's say I have 4 disks. Three of the disks will be storing data, and the 4th disk will be storing parity, which is an XOR of the data that I just stored. And of course, the parity is not dedicated. It's not one disk dedicated to parity, but I'll keep moving the disk in a round robin fashion. And then what this RAID 5 gives me, it gives me the ability, if one of the drive fail, I can reconstruct the drive that's failed. So for example, if disk 2 fails, I can reconstruct the value of B by XORing A, C, and the parity. And this will gives you back the value of B. Okay, so I can afford to lose 1 disk in the disk array. So that's what basically the RAID 5, the way it works. So you can, with the RAID 5, you have at least 3 disks. You keep striping the data across the disks, and you, for each of, for the number of blocks minus 1, let's say you have 4 disks, you stripe 3, and you compute the parity and put the parity, computed parity in the 4th block, in the 4th disk. And you keep doing this, and you don't forget to move the location of storing the parity bit in a round robin fashion. And this will basically give you the ability to lose 1 disk without losing your data. Yeah? That's basically RAID 5. Now, this is to summarize the comparison between the different RAID levels. So RAID 0 is striping, which means I take the blocks, and in a round robin fashion, I keep writing them to my disks. So the minimum disks I need is 2, and the capacity, the overall capacity of the RAID is the number of disks times the disk capacity. Now for RAID 1 is mirroring, which means I write the same blocks to 2 disks. Of course, in RAID 0, if I lose 1 disk, I lost my data. In RAID 1, I can afford to lose 1 disk. And I'm not, in terms of capacity, is the capacity of, I get the capacity of 1 disk. The write will not be improved. The read can be improved because I have multiple copies of the same disk. Now for RAID 5, it needs at least 3. It needs at least 3 disks. So whenever I write some blocks, I also XOR them and store the computed value of XOR in the blocks. It's called the parity. I store it on one of the disks, and the disk where I store it, I keep moving it in a round robin fashion. So basically, the capacity of this RAID 5 is the number of disks minus 1, because 1 will always be stored in the parity, not fixed 1. Of course, the parity is this disk where I store the parity keeps moving. And so the overall capacity of the array is the number of disks minus 1 times the drive capacity. Now, RAID 6 is similar to RAID 5, except I keep 2 parity bits. So I keep basically, I keep computing 2 parities, and I keep a copy of 2 parity. I keep the parity, 2 copies of the parity. In this case, I can lose 2 disks without having a problem. Okay. So these are the basics, the basic RAIDs 0, 1, 5. Those are the most common ones. The other thing that come to mind is that you can combine those, you can combine these RAIDs into other configuration. You can compose them. So for example, a RAID 10, also known as RAID 10 plus 1. So what you do is you first do RAID 1, which is mirroring. So you have two arrays. Each array is inside the array you are doing mirroring. So that's RAID 1. And then there's two sets of mirrored disks. What you build on top of them? RAID 0, which is striping. Yeah? Are you following? So in here, I am doing mirroring. Can you see A1 is stored in 2 disks, A3 is stored in 2 disks, and so on. And so in here I can afford to lose 1 drive on each side, and I will still be fine. I hope that I won't lose. Let me see. I won't lose 2 drives in one set. Then it will be a big problem. Yeah. So you can combine. You can also do RAID 0-1. 0-1, which means you do striping, then mirroring. Okay. So you can have those configurations. In here, just be aware of this. There is, of course, lots more details to this. A lot of products out there that you can buy and configure. But you cannot talk about database storage without at least mentioning RAID. Very, very important technology used in practice. So the choice of the RAID levels that you will go for, or the RAID configurations that you go for, is based on the costs, based on performance that is desired, and based on the risks that you can take, the importance of the database that you're trying to manage. So the more sophisticated and more advanced RAID configuration, of course, more costly to maintain, more costly to set up. The other thing we need to be familiar with, at least to be aware of when it comes to database management and storage management, is something called SAN, Storage Area Network, SAN, and NAS. Very important technologies when it comes to storage management. So traditionally, you have a set of servers, and each server has its own attached storage. That's one way of doing it. So you have, for example, Banner server, and it has its own database and its own storage, attached storage. There is a Blackboard server. It has its own database and this database server has its own storage. So you can see here, every server has its own storage. That's one way of doing it. This is directly attached storage. But the problem here, this could be very inefficient. So some servers have very high usage, and they might need more disk. Others very low usage, and that capacity is basically wasted. So you have inefficient resource utilization. You can be, in many cases, underutilized capacity. Plus, if you have backup and restore and managing the data, you have to replicate that solution you are using to backup and restore, and keeping a watch on the storage and monitoring the storage. You have to do it on multiple servers. Okay. Why can't you just take those storage and consolidate them and manage them in one place? That's what this network attached storage and storage area networks are used for. Okay. So the first one is called SAN, and the other one is called NAS, and a huge difference between the two. These are two solutions. When the vendor comes and knock your door and say, okay, I have some storage solution to sell you, they will say it's a SAN or a NAS. Sometimes it's combined. At least you should be familiar what this means. Okay, so in a SAN, what we have is we have some dedicated storage server, and this dedicated storage server is connected with our servers using a special network, not the normal network. You have the SAN server or the SAN storage solution, and you have your servers, maybe Banner server, Blackboard server, ERP or SAP server, and so on. So what you do is you connect these guys through a special high-speed fiber optic channels, very high-speed network. And basically what we have here is that you start allocating some parts of the SAN to each of those servers, depending on the need. And basically this storage is known as block-based storage. And this is what we need for database. So for database solution, you should not go for a NAS. You should go for a SAN solution, because SAN supports block-based storage. You can manage the storage at the block level, not at the file level. Okay. For example, in some solution like Dropbox, which is a network-based storage solution, it manages storage at the file level. So the unit of reading and writing is a file. The unit of management is a file. In here, the unit of management of this reading and writing, the unit of reading and writing is a block. And the database, that's what it does. As I will explain shortly, the database is made up of files, and files are made up of blocks. And what database is really doing is reading and writing blocks. So this type of storage is ideal for a database solution. But of course, much more expensive than a NAS. So every server will have its dedicated access to a part of a NAS. So it's, to summarize, part of the SAN. The SAN is a solution to consolidate storage. So instead of having every server its own storage, you consolidate it in one solution, and then you go and allocate storage to each of the servers. Of course, the SAN box, and which is typically a special hardware with special operating system. When usually it's sold as one piece, you just bring it and plug it into your infrastructure and connect it with your servers, not using Ethernet. You must use much higher speed network, dedicated network, not a network that is shared by other users to send emails and watch YouTube and so on. That will not work. It has to have a dedicated network connecting your SAN box with your servers. Okay, then you have very, very high speed, excellent solution for database. The other solution, kind of cheap one, is more a NAS solution, which is known as network attached storage. In here, you can think of it as a file system. It's nothing but a file system. And the users will see this as a drive. You go and map it, you add it to your, let's say, Windows Explorer, and you can read and write files. So it's excellent for managing files. Within an organization, if you have some shared files, so instead of course, everybody will have their own local files, but if you want to have organization level files where you want to manage files, then you go for a NAS solution, network attached storage, much cheaper than SAN solution. Yeah, and in here, how your NAS and workstations or servers are connected, using the normal LAN. You don't need a dedicated network for this to take place. You can already see the performance is much lower than the SAN. Yeah, so those are the three major storage solution used in practice. In practice, you will not find a real commercial important database running on single disk, normal disk that we have in our laptop or desktop. Yeah, either they are running on a RAID or running on a SAN, dedicated SAN box. Okay, and that SAN box is linked to the servers using high-speed network. Is clear? At least kind of awareness. Being aware of these technologies is very, very important. Okay, moving on. What I want to discuss now, yes, please.
For this kind of NAS,
Yeah.
for a program, does it make a difference when you are using this?
None of this is visible. I worked as developer and database developer and software engineer. Never seen any of them. I see them in these fancy data centers and so on. I went there multiple times, but it makes no difference to us as developers. DBAs, of course, they need to be aware of all of this because they configure this. For example, here they configure how many terabytes do I allocate to BAN and how many terabytes do I allocate to Blackboard, worrying about the physical connection between the SAN and the servers and so on. But us as developers is totally transparent. Whether the database is a poor man database writing to a disk or writing to a disk array or writing to SAN, no difference whatsoever for us. Sorry?
If you want to access a physical file from a program, will it also make a difference? It will be the same?
Okay, now in here, good question. I will be answering it shortly. So in that database is made up of one or many files, and these files, the database is responsible of managing internally. Even the operating system, for the operating system, those files are black box. For us as developers, those files are black box, and you can't even get to them. Okay, so what I mean here, the SAN, as I mentioned before, the SAN is block-based storage. You allocate some storage space to the database, and the database manages it, not the operating system, not us as developers. Okay. For the NAS, this one you see it as if it is a drive, as if it is a drive in your machine. In fact, it has a long time since I did this, but you can map a drive. I forgot how to map a drive. You can map a drive and I'm not sure. Map a network drive. Can you see it here? Map a network drive, and then you can specify the location of your NAS server, and then you can access it. Yeah, it's basically a huge, humongous space, disk space that looks huge and logical, but behind it there is these NAS server serving these files. Yeah, so even as developers, if you want to read and write, you will see it as a drive with folders and subfolders and so on, and you can manipulate the files. Yeah, for SAN, you might see files there, but those files are black box for you. You don't manage them internally. It's the database that takes care of managing them. I hope that answers your question. Yes? Okay. Of course, internally, SAN and NAS, they might use the RAID internally and some other techniques, but that's a different story. Usually those are off the shelf. In practice, those are off the shelf solutions. You just buy them from IBM or Dell AMC. There are major storage vendors. You just take it, put it and configure it and connect it with your infrastructure, typically. Okay, and it comes with its own management software to back up, to restore, to increase capacity, and so on. Okay. It's not something you will build yourself from scratch. If you want to build things from scratch, you will go for RAID, and you do it kind of yourself. You configure it yourself and so on. But for these are already pre-built solutions. Okay, now for database file organization, we will now open the storage engine and see really how it works and how it stores the actual data in files. So in database, there is no magic. We still have files, but just these files happen to be managed, and we read and write to them in very, very smart ways. And that's what this discussion will try to highlight. So when it comes to storage, database storage, or the storage engine, it addresses two problems. Two problems this engine tries to address. One is how do we represent the data physically on disk? So the database is made up basically of one or many files. So database is made up of one to many files. Yeah. These files are black box for the operating system. Operating system does not manage them, because database has a lot more knowledge for it to manage these files in a much better way. And I will explain this as we move forward. The other thing is these files are made up of one or many pages. So file is made up of page. Another name for page is block. So these are synonyms. If you hear block or page in the context of database storage, they mean exactly the same. Okay. Inside this file, what you will find? One or more record. Yeah. That's basically how the database stores the data. Stores them in files, and files made up of pages, and pages, that's where we store the records. So the database storage need to decide whether it creates one or many files, need to decide the page layout, how this page will be organized, and need to decide the record layout, how the record will be physically stored and organized and laid out on the pages. That is the concern of the storage manager. The other concern is how to efficiently move data back and forth from memory to disk. So two roles of the storage engine. One is decide and take care of storing the data physically in files, in pages, in records in those pages, and also how to efficiently move data from disk to memory and from memory to disk. Those are the role of the storage manager. Okay, now this is what I just explained. So database made up of files, and the OS does not know anything about these files, does not go near them. It knows that there is file, but inside the inner working of these files, writing and reading to them is taken care of by the database. So these files are made up of pages, and a page has a sequence of records, and of course a record is a sequence of fields. A record means a row in a table, and a row has multiple fields. And we will see the details how each one is managed. Okay. Okay, so I think this is what I just explained. So the storage manager is the one that creates these files in the first place, keep them organized in terms of pages, in terms of pages, and also keeping track of the available space in every page. So let me show you now. Let me do some little animation here to make it clearer. Okay, so this is how it works. So the most common organization, so we have a disk, and in disk we have the database file. So in the disk we have not sure if I can write. No. Unfortunately, I cannot write on the screen now. Okay, so what we have here, our data file, how the data file is organized into pages, multiple pages. And each page has a header and some data. We will see how the page is laid out, what's the content of every page. And then we have this very, very important dictionary. What do you think this dictionary will have? Sorry? Very good, basically. So very good. So we have ID, we have a logical ID. So every page has a logical ID. And what else? A physical address. Remember, at the end of the day, this page will be living in disk, in certain track, in certain sector. So it has a physical address. So what this dictionary does, it contains basically a simple dictionary. The key is the ID of the page, and the value is the physical address of the page. Yes? That's the first level of organization. So the first level of organization, our database is made up of one or many files. Each file has many pages. And these pages, there is very important dictionary that keeps track, basically maps the logical address with the physical address. Now the rest of the database only knows the logical address. It does not need to care about the physical address. So if these pages move around, or some of them are moved, remember, database administrator is recommended that they keep the pages contiguous and they keep things organized. So the mapping between the logical and the physical can change, but the rest of the database is spared from this. It's not, these changes are not visible because the rest of the database only aware of the logical address. So in here at this level, when I want to read certain page, I basically I will ask the buffer pool to go to disk and get me the page. Yes. So for example, let's say someone is asking, which is typically the query execution engine, is asking for page 2. The query execution engine is asking for page 2 because this page 2 has the details of customer 1, 2, 3. And it wants to retrieve page 2. So what will happen? What do you think?
ID of the page?
We know the page ID is page 2. So how we will get this page from disk? From where we will get the physical address? From the dictionary. So what do you think we will do first? Read the dictionary. So that's the first step. We read the dictionary. And usually, what do you think this dictionary, if the buffer is smart, it will not throw this dictionary. It will keep it in memory as long as because it will be heavily used. So a copy of it usually will be kept in memory. So it doesn't matter. But at the end, we will read the dictionary, and then we will look up the physical address, and then ask the disk manager to get us that particular page. So it's a two-step. We get the dictionary and then we get the actual page. Then once we get the page, then what we do, we give a pointer to the caller, because this one now is in memory. This page now is in memory. and we say to the caller, most likely is the query execution engine, we say, you asked for page 2, here is a pointer to page 2, this is a location in memory, go and help yourself. And the query execution engine will go through the content of this page. Okay, how it will know how it will know how to deal with this page, it needs to be familiar with the layout of the page. It will come. So what I want to say here, at this level, what we really need to understand, the data file, the database file, is made up of pages. And these pages, there is a dictionary that keeps track or maps the logical address of the page to the physical address. Whenever somebody requests a particular page, we look up the physical address from the dictionary and go and get the page and hand over a pointer to the page to the requester. Okay? We all know this because we cannot work on the disk directly. We have to bring the data we want to the memory first. Okay. So the database does not rely on OS to do this exercise. It just asks initially when you create a database, the database will ask the operating system, please create this file for me, and that's it. From that time onwards, it's the responsibility of the database to read and write and maintain that file as a set of pages. Okay, so there is almost no database out there. Most of them they don't rely on OS to manage the data inside the file. And the reason why is that the database can do a better job because it has much more information about the database. It knows, for example, let's say which pages are more heavily used than others, which queries are executed more than others. It maintains statistics about each table, how many pages it has, where what is the range of each column, especially the key columns. We know the range. For example, if you have a student table, we know the range. For example, what are the students starting with A? Database has an idea, has an estimate. How many students with names starting with A? How many students with names starting with B? So database maintains a lot of metadata and a lot of knowledge that it can make use of during the query processing and during reading and writing. And the operating system does not have this knowledge. Because it lacks this knowledge, it cannot do a better job compared to how database will do it. And this will become more apparent as we move forward. So for example, here, in this buffer replacement policy, like when we read some pages on the buffer, which ones do we eject first? The operating system will have no clue because it doesn't know which ones have been used before, which ones are more likely to be used in future queries. But database has some knowledge that it can make use of to make better decisions in terms of buffer management. Okay. All right. Okay. So that's the main message. Main message, the database takes care of managing the inner working of the files used for storing the data. Now the pages, let's talk a little bit about the pages. So the database pages are fixed size, as I explained before. Fixed size between 4 and 16. For example, DB2, Oracle, SQLite, they use a page size of 4 kilobytes. The SQL Server, Postgres, they use 8 kilobytes, and MySQL use 16 kilobytes. Okay, and these pages will be containing blocks, metadata, indexes, log record, anything the database maintains at the end of the day is stored in pages. So database does not only take care of data. We have metadata. What I mean by metadata? What could be an example of metadata? For example, the schema of the tables. That's metadata. Statistics about tables. How many records the table has. How many, as I explained, the distribution of the values. For key columns, what is the distribution? For example, if you have a salary column, how many people within let's say 20,000 to 40,000? How many people 40,000 to 60,000? Database has knowledge of this because this knowledge will be very helpful, as we will see later, in query execution. So database has this knowledge. All this metadata gets stored on pages. So pages are not only stored in data files or data itself, it could be stored in metadata, it could be stored in indexes. Indexes, we'll spend a lot of time discussing indexes. Any idea what's an index? Similar to what you have in the back of your book. What do we have in the back of the book? Last few pages? An index. For each keyword, the pages where we can find some discussion about those keywords. Okay? Why we have indexes in the back of the book? We can jump quickly to the sections or the paragraphs or the pages discussing particular concept. So same thing, in database we will see we can create indexes. And those indexes will need to be stored on disk. And they are stored in pages. Also the log record. Remember log? We will see this, of course, in more details. But anything you do in database, there is a log get created. If you update, for example, you update student sets the phone number equal the new phone number, that change is logged. And that log is also stored in pages. So page is the unit where everything gets stored in the data. So each page has a unique identifier. And basically the database maintains this dictionary that maps the logical ID of the page with the physical address. This dictionary is a critical component. Okay, it's clear in terms of file is made up of pages, and pages are uniquely identified, and the mapping between the logical address and the physical address is maintained in a dictionary. That's basically the idea. That's the first level of organization. File made up of pages, and pages are made up of, we use them to store records. So now let's look at the page. So the file organization is clear. The file organization, this one, this level.
Dictionary or
directory? Directory is the kind of the same name, kind of same concept. It's at the end of the day, it's a map between a logical address and a physical address. But a directory is the more common term used in this context. Now, in terms of organizing the data inside the page, there are many ways of doing it. The most common way is a heap file. A heap file organization. In a heap file organization, which is the most common, what we do is the records are not stored in any particular order. There is no order. They are not sequentially ordered. We can also have sequential or sorted data file organization. This is not really in here. Usually, if we want to do this, type of organization, we create what is known as a B+3 index. We will not discuss this here. It will be a full lecture just on this. This data structure is so popular if you want to store your data in a sorted way. If you want to keep an order, you want to store the data in a sorted order, you need to use some kind of data structure named, typically known as a B plus tree. The other very common organization is a hashing file organization. You know hash, what is a hash table or a dictionary? In some languages we call it dictionary. Key and value. Yeah. So we will discuss next, hopefully if we go through what we have today, next session will be more in hashing and how we create a hashing file organization. But for now, let's just focus on the simplest one, which is very commonly used, which is the heap file organization. So heap file, it has an unordered collection of pages. The pages are not really ordered in any way. And the heap file supports this operation. What you can do with the heap file, you can create a page, you can read a particular page, get a particular page, write a page, delete a page. These are the operations you can do. You can also, of course, iterate through all the pages. That's what you can do when you organize your file, when you organize your data in a heap file. So imagine this imagine this file is the organization is using a heap file. What you can do, you can read you can get particular page, you can write particular page, you can delete a page, or you can iterate through the pages. Those are the operations you can do on a heap file. Okay. And then, of course, for example, if you want to iterate through the pages, how can you know what pages you have? If you want to iterate through all the pages in your file, you need to have the page directory. This one plays a major role. This directory plays a major role in here. If I have a logical address and I want to know the physical address, I do lookup on the directory. If I want to iterate through all the pages, I do lookup on the directory. So the directory plays a major role in a heap file organization. Okay, now now let's see. Yes. So that's what I just explained here. So you must maintain in a heap file, you must maintain a directory. This is an essential data structure that you need to maintain to be able to map your logical address to the physical address, and to be able to also know the free slots. So this directory also maintains some metadata. So for each of the pages, it knows the free slots or the free space in each of the pages. So if there is a new insert, it knows which lucky page that will receive the actual inserts. Okay. Of course, these pages are belonging to one particular table. So each table will have associated pages. So it's not like page we store all the data belonging to other tables. So page is dedicated to one particular table. And if it needs more pages, it will create more and more pages. Yeah. So as you can see here, when I create more pages, and if these pages belong to the same table, these pages might be created somewhere else. And I lose this contiguous. Remember the contiguous blocks? That's why periodically I have to run some kind of routine, usually at night when the database is not busy, to reorganize things and to keep the blocks that are, or the pages that are belonging to the same, let's say, same table or same index, to keep them physically close to each other, to reduce the seek time when we want to read from them. Of course, I don't do this reorganization online in the live database. I do it either when the database is not that busy, or schedule it as a maintenance job at night. Okay, Now, if I go inside the page, if I go inside the page and start looking at the inner working of the page itself, I find that the page has two parts. There is the header and there is the data itself. What I find in the header is the page size, the checksum. Let's say if I restart the database and make sure that every page is not corrupted, I can do checksum compute, which is basically a function that I compute over the data, create some value and store it in the header to make sure, to be able to verify that there is no corruption in the page. I might also store the DBMS version. So it has a lot of metadata. Among it is this. If there is any compression here, if I'm compressing some of the data stored here, the compression algorithm and the compression details are stored in the header. So the header has some metadata about these pages, this data that is stored here. Now, inside this data, this is the most important part. What I'm storing in this data, typically what I'm storing? The records. Thank you, the records. Now, the way I store records inside the page, there are at least, these are the three major ways of doing it. Three major ways of doing it. There is a row-oriented storage, column-oriented storage, and log-oriented storage. This is important to understand because you might come across this in your reading, because these are different ways of storing the actual data inside the pages. Three approaches: row-oriented, column-oriented, and log-structured model. Okay, three ways. So let's look at these three ways. The first one is row-oriented. What does that mean? What do you think? So remember, tables are made up of columns and rows. Okay, so row-oriented, yes, we store row together. So pages will be storing set of rows. Now, what do you think column-oriented? So pages will be storing values of one particular column. And what about the log-structured storage? We don't store no rows, no columns. What do we store? No, not pointers. The actual inserts and updates and deletes. The actual log, the actual changes. You can think of them, okay, I inserted some record and these are the values that I insert. Then later on I updated some of the values. And later on I changed my mind and deleted the whole thing. So I keep track of the changes. I store the actual changes. The actual, think of them as the changes. Sorry?
Like the secure statements.
You can think of them that way, like the SQL statement that created the data or updated or deleted. Yeah. So I will give some further explanation to each of them. So let's start with a row-oriented model. A row-oriented model. In the row-oriented model, there are many ways, but I just followed here the most common way and the most popular way of storing rows in a page. The most common way is known as slotted pages. The most common way of writing records in a page is to use this slotted pages organization. What this slotted pages is, you can think of it as two arrays. One growing this way, this first array is growing this way, and the other array is growing the other way. And they keep growing until there is no more space and the page will be full. Okay? So what I have here, in here what I'll have basically the record ID in this array, the slot array. So I have two arrays in the page. One is called the slot array, and the other one is basically the records array. So in the slot array, I have the record. Every record has a record ID. and then the offset where that record is stored. So if somebody is looking for particular record ID, they will know from where to start to get the actual record. And then the next record the next record is storing the offset of the next record. So you can think of it similar role to the dictionary at the file level. So in dictionary, I have the logical address of the page mapped to the physical address of the page. In the slotted array, what do I have in the slotted array? I have the record ID, which is a logical identifier of the record, mapped to the physical location in the page. And the physical location is computed in terms of offset. Yeah. And I start recording, you can see here I start recording from the end of the page. So you see here the slotted array is occupying the top of the page, and the actual data is occupying let's say the bottom of the page, and they keep growing until they meet each other, until there is no more space. And this organization basically supports variable length record. Remember, you're already doing, some of you are advancing your data model. Lots of the columns are variable length columns. Whenever you do varchar 50 or varchar 200. In here, because you can have a look here, you can see here these are variable length records. So we need to, if somebody is looking for particular record, they need to know the record ID, and from the record ID we can jump directly to where to start reading the actual record. That's basically the most common organization. And in the head, what we find is the number of used slots, how many slots are used, and the offset of the starting location of the last used slot. We also maintain where is the last used slot. So when there is a new slot to be inserted, we just jump to the last used and right next to it. So this slotted pages organization is the most commonly used when we talk about row-oriented storage. So we maintain an array on top of the page that keeps track of the record ID and the offset where we will find the record on the page. The offset, imagine this is your page, okay? And the page has, let's say, lines and columns. The offset, maybe it tells you, okay, if you want record number 10, go to page 5, column 10. You will find it there and start reading from there. Yeah? Same if you want record 20, go to line 12 and column 6. You will find your record there. Yeah. Now the record might have a header that will tell you the full length of the record. So to tell you where to stop. So the slot might tell you where to start, and then when you arrive to the record also has a header that tells you the length of that particular record. So you know where to stop reading a particular record. Yeah? So that is basically the idea. And the idea here, you can see here, outside the page, they are not aware of where is the physical location of the actual record. Outside the page, they only know the actual logical record number, record ID. There is no, the actual physical location within the page is not visible outside the page. You come to the page, and then how do you find where is the actual record I'm looking for? By looking it up in the slotted array. Is clear? Okay. Now moving on here, the other organization is the log structured organization. log structured organization. In here, what we do is we keep appending to the page, we keep appending the log records. For example, something like this. I'm inserting some record with ID 1 and the value A. Let's say this table has only two columns, ID and val. So in here I inserted another ID, deleted 4, and so on. So I updated here, I updated the val, set it to X where ID is 3. And updated val, set it to Y where ID is 4. So I keep track of the changes that is happening to my table. Okay, I don't store the actual rows or columns. I store the actual changes that are taking place. So this is super fast when it comes to insert. You just appending all the changes that takes place. And many databases, in fact, are using this, especially Apache, HBase, Cassandra, RockDB, LevelDB. All of those are using a log structured organization. Now, when I want to read, what do you think? How I will be reading the record that I inserted this way? Bottom up. So I'll be reading bottom up and reconstructing basically the image of the record. And plus, not only this, typically, you can also define indexes. Indexes, it gives you for each ID pointers to the log statement related to that particular ID. So you can jump to them much quicker. Another way to do it is periodically you can compact the log. You can compact all this and give the final snapshot image. We don't need to keep track of all these logs. At a certain stage, we can truncate all and just give the final values of each of the records. Yeah. By the way, this type of organization is used by GitHub. You know, when we are doing in GitHub, when you are doing GitHub and basically changing things, committing, and when you commit something, what GitHub is keeping track of the set of changes that you have done, the delta of the changes. So it's keeping a log of the changes that you did. That's why you can basically switch to any version that you wish in GitHub. You can go back in time to different versions and roll back and throw away some changes that you did before. Because it's not storing the latest version, it's not storing the row or the columns, it's storing the actual changes, the actual deltas that you are doing. Yeah? Yes, please. Very good. It is fast in writing, but slow in reading. But you can enhance the reading with two things, as I mentioned here. Either by using indexes for each particular ID. It has pointers to log entries related to that particular ID. Remember the index, similar in your book. You have a term and you have the pages where you can find discussion about that term. Same thing here. You have the ID of a particular record and pointers to all of the log entries that are related to that particular ID. And then you can go through and reconstruct the record bottom up. Yeah? Okay. Or you can database periodically when it's not busy doing nothing, it can go ahead and compact the records. Yes? Using the latest values. For example, I inserted a student and the email was student1@qu.edu, and then I changed later to be let's say my email at qu.edu. Then when I compact, I don't need to keep the previous version. I just keep the latest values. Yeah. And this way, if somebody comes and asks me, I already have all the values already done. So this way, you have a balance. In terms of write, super fast because you are just appending logs. And in a reading, I can make it super fast by periodically compacting the log entries.
Which one is better, row or column or block structure?
Okay, very good, very good. Depends. I will be explaining this more. It's coming. Let us first understand each one, and then we will discuss in which scenarios some of them are better than others. First of all, this log record, sometimes the file system you are using, some file systems, they don't allow change in blocks or change in data once you create a file. You can only append. Yeah. So if you are using, these are special type of databases. If you are using maybe some of you might be familiar with, there's a file system called HDFS. Yeah. Some of these databases are using HDFS file system. HDFS file system is an append-only file system. You cannot change things. You can only keep appending to the file. You cannot change. So this log structured organization is the only way possible to basically build a database on top of HDFS. Why we build HDFS? Why one would build the database on top of HDFS? Because HDFS, you can have a storage that is on multiple servers, consolidate all this storage and make it look like a one big logical disk. Yeah, and you can have replication and you can have redundancy. HDFS will do all of this for you. But what is the limitation? What you put there, you can only append to files. You cannot modify blocks within a file. So you are forced to do something like this organization. Yeah. Okay. Now, in terms of record layout, now suppose I get a record. Suppose I manage to, I know the record ID. I went to the slot array. What the slot array told me, go to this offset, you will get your record. Now I have my record at hand. This record is what at the end of the day? It's an array of bytes. When you retrieve it from disk, at the end is zeros and ones. Yeah. Now, how the database will make sense of it? How the database will parse it? Another technical term. How does it know? Okay, this is the ID. This is the first name. This is the last name. How, from where do we get these columns or the schema?
We keep some sizes for each.
And how do we know the sizes of each column? Some metadata. Where is this metadata stored? Sorry? In the header. No, we don't store this in the header, by the way, because that will put a lot of overhead. Because we have all this record, they have all the same schema. Why should we put this in the header? No, not in the index. No, there is a special database. Typically, every database has a special database named as a catalog. The general term for it is a catalog, where it maintains all this metadata. So the schema of the tables. It maintains the access rights. It maintains the statistics. Like, for example, how many records in each table. How many, as I told you, the data distribution in the key columns and so on. So all this is maintained somewhere. What is this somewhere? It's a catalog database. So basically, when you get a record, you need to know for the reader or for the recipient of this record, they see it as an array of bytes. They need to parse it. They need to make sense of it. And for them to make sense of it, typically the query engine receives this record. And how it makes sense of it, it needs to get the schema of the table related to this record. And from where we get the schema of the table? From the catalog. Okay. Now, once we get the schema, then we can parse this. We know that this one is an int, and we know the size of the int. We know this one is string, varchar or char, and we can know. For varchar and char, they will be like a delimiter, maybe a null terminator to know that the string has finished, or the varchar has finished. Or it could be that in the varchar, in front of it, we store the length of that varchar, the actual length of the varchar. Depend on how database does it. So at the end of the day, when we get the actual record, it's nothing but a byte array for the query execution engine to make sense of it and to parse it and to know which part is which. It needs to get the schema of the table. And from where to get the schema? From the catalog. Is clear? Okay. Now, just one more thing I want to highlight here, that every record will have an ID. This is not the primary key that you created, or let's say student ID or customer ID. No. You can have your own primary keys, doesn't matter. Database internally creates a record ID for each of the records. And typically, the most common way of doing it, the record ID will be the page ID plus the slot ID. Remember the page? So the file is made up of pages. So the page where the record is stored, the page ID, the logical page ID, plus the slot ID. Remember at the page level we have slots. So the combination of page ID plus the slot ID can be used for record ID. Okay. So that's the page layout. Now comes the question of storing large values. Sometimes you have varchar max, like for example in SQL Server that I'm familiar with. You can have varchar max, which could be megabytes or even gigabytes of text or binary. Now the page might not, that particular column might not fit on one particular page. How the database deals with the situation. So it will create an overflow page. And the value of that particular column will be pointed to another page. And that overflow page, if the content is too long, you can have other linked overflow pages. So when somebody is looking up and getting the value of particular column that is long, we might need to jump to other pages to retrieve the actual values of that particular column. And in the record, it will just have a pointer to the page. Yeah, this is how database deals with any records with the size that exceeds the size of the page. If the size of the record exceeds the size of the page, there's no other way to do it except to do an overflow page. So the record will be pointing to other pages, and that page can also be linked to other pages if the record happens to be very, very big. Yes, it's clear? Okay. That's one way of doing it. Yes, please.
Multiple pages, and between them there is pointer.
Yes, they are linked pages, basically. Linked pages. Yeah.
So, Dr. C will be, you mean C is large value, right?
C is large value. Let's say a web page or a Word document or some large text. Let's say some Wikipedia page. It's stored in the database in particular column. Let's say the article details column. So it's spanning a lot. Let's say the page has 1 megabyte, for example. Okay, and remember that column, the article has, let's imagine 1 megabyte, and the page. You remember the page size? 4K is 816. So definitely cannot fit on one page. So what we store in the record, we store a pointer to an overflow page, and then we store the values of large columns in there. And if the column does not fit on that overflow page, we can have multiple overflow pages linked together. Once we land in the first one, we can link to the next one and keep moving that way. Yes?
So I mean, in field, in the column, there is no value.
There's no value. There is what?
Or the pointer.
There's a pointer to a page. A logical, remember, a logical address of the page. From where we will get the physical one? From the page directory that we maintain at the file level. Yes? Yes, please.
Who took care of this? The developer or the
No, database takes care of all of this. This is all transparent. You don't see this. Yeah? But you need to be aware of it, that there are overflow pages when the record does not fit on a page. Yes, please.
Like for common database like Oracle, when they use below field,
Yeah.
it is same.
In here, each database has its own rules. For example, let's say maybe SQL. Let's say MySQL might say if a record occupies more than half page, we will not store the whole value inside the page. You know what I mean? So there is some threshold. It's database specific. This is the implementation details of the database. The database might say, if I have a record that is occupying more than half page, I will kick out the big columns into overflow pages. But although you might define it as a blob or you might define it as a varchar or var binary, you might have a small data there. So we will not put it in an overflow page. So the database will have some threshold. Or some other databases like SQL Server says, as long as I can fit it on one page, no problem, I will keep everything together. If you give me something that I cannot fit on one page, then I will use overflow pages. So this is database specific, the way they do it. But usually in the documentation, they will say so. They will explain what strategy they are using. Now, another thing to keep in mind, some databases allow you to store large objects outside the database. So in SQL Server, this is something called file stream, and in Oracle, this is called B file. So what this means, the actual data will be stored outside the database in a file system. And what we have in the database is just a link to that file. Now, in here, you need to be very careful. This database external, now it's external to the database. You don't benefit from durability, you don't benefit from transactions. This is outside the control of the database. There are no guarantees there. But the advantage is those files, you can manipulate them from outside the database. You can open, let's say if it is a Word document, you can open it in Word, no problem. Database is aware of it, but it cannot change it or access it or provide you durability or provide you transaction properties that we discussed. Yeah? Just be aware of this, that database has this, some databases have this feature. This is different than this. This is very, very different. In overflow pages, these are under the control of the database. You have durability, you have transactions, you have nobody can access this directly. It's under the control of the database. In here, this is outside the control of the database. Yeah? Okay, one last thing. Before I cover this, let me show you the column-oriented storage. The column-oriented storage. In the column-oriented storage, you don't keep the row together. The page will store the values of a particular column. Yeah? So in a row storage, you keep the columns of a row together and you store them contiguously. In here, it's very different. Now, you might ask, as I think one of you asked, when do we use which? Now, to understand this, you need to understand two major types of workload. In database world, there are two types of workloads or two types of usage, let's say, two types of database usage. There is online transaction processing and online analytical processing. Okay, online transaction processing is for short, small queries that usually affect small number of rows and usually touch one entity or few entities. Yeah, and this is usually like, for example, if you are using something like Banner, you are just adding a course, registering a course, dropping a course. Those are small operations. For online analytical processing is usually big read queries that may be going through the whole table or doing lots of joins sometimes. Let me give you an example. Let's say you have a dashboard in the executive office or in the president's office saying, okay, let us see what is the, let's say, average GPA. Those are some performance indicators, average GPA. Now, this average GPA, to compute it, you have to go through all the, let's say, all the students and basically go through the .gpa column and summarize it. So when you are doing that computation, you don't care about other columns. It will be very wasteful to get all the rows that has all the columns just to compute the average GPA. Wouldn't it be better if the GPA was stored in its own pages and you just get a couple of pages, just getting the GPA and then summarizing that data? It's much more efficient. So typically in high level, the OLAP column-oriented storage is more optimized for OLAP workload, for analytical processing workload, when you want to do reports, summary reports. And OLTP, the row-oriented storage, is much more efficient because usually, for example, you are getting your student details in one go. Most of the columns you are getting them. So if you want, in column storage, if you want to get all the columns and reconstruct the rows, of course, it's much more expensive. So each one is optimized for different workload. That's what we call workload. There's an OLTP workload, and there is OLAP workload. Column-oriented for OLAP and row-oriented for OLTP workloads. And recently, a lot of databases, they are hybrid. You decide whether to use column-oriented storage or row-oriented storage. Okay, I think this is what time allows us. Yes, please.
So the table could be stored in multiple pages, right?
The table, definitely in a large table, yes, of course, multiple pages.
So we should keep track of the last row if it is row-oriented, or maybe the column also is distributed, right? This has many rows. So many cells. Yeah.
Okay.
So we need something to keep track of the end of the column or the end of the table to reach the last row. Because
you're talking about column-oriented storage?
Both. If it is rows, we need to keep track of the last row on the table, so we don't reach all pages on the to look for one row, right?
No, okay. No,
so
basically.
The page may have many rows, right?
The page will have many rows.
Maybe if I want to make like a query of selecting something from the whole table.
Okay.
So I need to keep track of the last row on the table. So I just stop on one page, and a certain page to not like go to whole pages, wasting the time. And even if it's column, I need to know that the last item or the last report on the column, so I don't reach other pages.
Okay. So in my basic understanding, is this. So you see this organization here. You have your pages. I'm sure the database keeps track of which pages belongs to which table. That's for sure. We know that is for sure. Pages belong to a particular table. Now, when you do select star from, let's say, customer, then what we will do, we'll go to dictionary and get all the pages belonging to the customer table. And we We bring all these pages to memory and we scan them one by one to get the details from the pages. So what I mean here, we know for each page, we know the pages belonging to a particular table, and we might know that from the file directory. We know the pages belonging to a particular table. Now, if we want to know what is in every page, we have to look at the slots of every page. The slot will tell us how many records are stored there, what is the record ID stored in that particular page, how much empty space available on that particular page. Then you take it from there, like depending what you do, depending what you are doing, depending what you are trying to do. If you are as we will see later on, some queries for them to be answered, you need to do full table scan. In this case, it's simple. For the table, you should know which pages belong to the table, bring every page and scan every page and retrieve from it the records. If you use in an index that we will see later on, if I'm looking for, let's say, student Ahmed, the index will tell me, go to page 10, you will find Ahmed there. Bring the page and then go through it to retrieve the record. So if I don't have an index, let's say you don't have an index on the book, and let's say you don't have even table of content, and you're looking for directory. You want to learn more about directory. How you will find the pages talking about directory? There's no way. You just need to flip through the book and look carefully. Where is the page? Does this page talk about directory? No. Move to the next page. So you have to do full scan. If you don't want to do full scan, you have to create an index, and that's what we will see. We will start seeing from next session. Yeah. So on top of this, you need an index to allow you to directly jump to the page where you should get the record that you are looking for. Without indexes, it will be much slower. You will have to do full table scan. I'm not sure if this answers your question, but
The index is saved on the catalog metadata or in the
no, the index, we will see different type of indexes. The index is basically the index at the end of the day will have the key value, the keys, and the pointers to pages. The index entries will be stored on pages. So the index will have a name, and basically many pages belongs to the index. But there are various types of indexes. We will see this. The indexing is very, very critical component of the database to speed up the query execution.